Good morning to all. So coming to this session, here are the fax devices. So while considering the fax devices in a transmission line network, so here we are considering the network that is here having the two generators, and it is both are connected each other, and it will giving the power to the load. Okay, here transmission lines are parallelly connected. Here we are considering the one transmission line having the one transmission line having the impedance of the x, and another transmission having the impedance of the 2x. So here what we have, so what we are considering that one transmission line having the x, another transmission line having the 2x. So whenever the impedance having the low path, okay, whatever the transmission line having the less impedance, okay, that will having the more amount of power. So whichever the transmission having the high impedance, that having the less amount of power. So here impedance causes the opposite flow of current in the transmission. So that will having the more. So if the transmission having the more amount of power transfer, it needs to be less impedance. If more impedance, less power. That's why here first transmission line one, here having the whichever having the impedance is x, that is flowing the power of, that is by 3, and flowing the method of the power. Okay, so this is about the power flow. So here this is it. In the period. So now coming to the, while if we having the, this is without the considering the passive. So while considering the transmission line, okay, with the one transmission having the HVDC line, another transmission having the ACL. So here having the HVDC line is nothing but here having the, we are considering the thyristor. So thyristor, what do you do? It will convert the AC to DC, and that way HVDC transmission we are considering between the one line is AC, another one is the HVDC line. So here high impedance, what having the high impedance line is having the less power flow, and less impedance having the high flow. So here high power will be flowed in this line, less power flow will take places in this line. Okay, that you have discussed. So similarly, we have taken the in this one mesh line. Okay, here we are discussing the parallel. So here we are going to discuss about the mesh system. What happened? So in the mesh system having the, we are having the two generators are both connected measured, okay, in a loop, and here it will be giving the power supply to the 3000 megawatts load. Here having the line, one transmission line the 1400 watts, and that having the, okay, so generator having the 1000 megawatts, another 2000. So the load having the 3000. So due to the impedance in this transmission line, okay, so this much of power is flowing, that is 1400 of power flowing, another line having the 600. So here what happened, due to the impedance in this transmission line, high amount of load is applied on this generator. Okay, so if it is less impedance there, okay, it will having the more amount of power. So due to the high impedance, what will happen? So load is take placing, okay, for the generator B. So if it is here, if you apply more amount of power flow, okay, we can reduce the power in this generator B. Okay, so without considering the fax devices. Now if you considering the fax devices, it will be like this. So here having the fax devices, so in this fax devices what we are doing, so here we are considering the same mesh loop, and we are having the, by using the fax devices, we are injecting the voltage with this transmission. Okay, what happen, whatever impedance that will be reduces, okay, that will causes the injecting the voltage by using the series capacitors. So what happen, the voltage is increasing. Okay, due to the voltage increases, what happen, the power also increase in this transmission line. Okay, similarly, so what happen, the line, okay, from the B to C is, the power flow is decreases, and the load of the B also is decreased. Okay, this is about the, without using the uh, fax device. Okay, with using the fax device, how it is, variation will be take place in a mesh loop. Okay, and so we have considered already what are the limitings of the, okay, load capability. Okay, how it is take places. Okay, that is thermal limited, the electrical stabilities. So in thermality is based upon the situations of the temperature, wind condition, weather condition, ground clearance, that will be factor will be take places while designing the transmission line. Okay, so while designing transmission, what we have to do, so we have to consider the three things, that is thermal capabilities, okay, electrical stability, okay, so stability of the delivery. So there are two types of stability, that is dynamical stability and transient stability will be there. Okay, so when due to the, if it is the sudden changes will be there. Okay, so sudden changes comes to the in this dynamic stability. So continuous variations is there. Okay, if you coming to the stability, so what will happen, that it should be having the in a sine wave. Okay, so if due to the variation, okay, so here stability if coming to the, there are two types of stability, that is steady state, transit state stability. So if we coming to the steady state, what will happen, so gradually the variation should be having the continuous. Okay, so whatever the power flow is there, that will be not in a same. So what will happen, it will vary with the high variation flow in the continuously. Okay, now coming to the transient stability, so in the transient stability, so what will happen, so it will be varied with the, due to switching sometime. Okay, so in the steady state, so it will continuously varying the power. Okay, in transit stability having the continuously variations in there. Okay, that we have to take place while designing the transmission. So limiting, we are having thermal limit is, dielectric limit is, and stability. Transient state, steady state limits and steady state transient. So both we having the there. Okay, we have to consider the both conditions in coming to the stability. Okay, now dielectric. So dielectrical material, whatever dielectrical material we are using for the in this transmission line generation session, okay, for the insulating purpose or cooling purpose, that should be having the same rating. Okay, not exceeds the rating. So it will have the 10% of rating above the ratings. Okay, if it is using the transmission line of the 400 kV, so whatever the dielectrical material used for the 400 kV, so it's having 10% of more dielectrical strength will be having. Okay, then only we can use the, it will be used for easy. Okay, now coming to the thermal capability. So in the thermal capability limits, what happen due to the weather conditions, okay, and temperature and wind conditions, what will happen, the effectiveness, okay, the effectiveness on the transmission is having the less. Okay, so effective way of a power flow in a line, okay, resistance impedance, that will also affect on the this coming to the this thermal capabilities. Okay, so we need to use here. Okay, you can see the transient, dynamic, okay, steady state stability. Okay, so if the frequency if not there, okay, so two transmission lines if not in, okay, in that coming to the bus bar and coming to the generator, so it should be having a, both are in, should be in a synchronism, so then only we can be transfer the power with the without affecting. So if it is frequency is not constant for the, not in a synchronizing for the bus bars and generator, what will happen, so it will collapse the total grid. Okay, that's we have to should take care while designing synchronization. Okay, we having the voltage. Okay, voltage should be having the same synchronous. Okay, so should be having the less or more. Okay, and there will be sub synchronous will be there while considering this one. Okay, now so here what we are doing, so here dynamic stability, so we are considering that here power flow and dynamic consideration of a transmission line. So here stability, here power stability here. Okay, so there are two types of power stability. Okay, power stability is nothing but we are having two types. One is transient stability, another one is a dynamic. Okay, so what will happen, well, coming to this one. Okay, so transient is nothing but it will coming to the when switching on, switching off. Okay, some condition. So dynamic means continuously it will flow. Okay, continuous, and it will be varied with the time. Okay, steady statement, it will gradually increasing or gradually decreasing. Okay, this will be happen. So now we are considering that dynamic stability. Okay, so here we are considering the two missions unlocked. Okay, here we are considering the two missions. So here generator 1 and generator 2. So here we are considering the two generators, that is generator 1 and generator. So here what we are considering, so one generator having the high amount of power. Okay, here we are considering this generator, that is generator 1 having the high amount of power comparing to the generator 2, that is sulfurous amount of power is transferring from the with here whatever the power is generated, okay, that will flow to the load side, and remaining power is transferred to the this generator also. Okay, so here having, and the generator 2 also having the load. Okay, so here it will both are interconnect. Okay, so both intercurrent. So if we take the line, okay, so phasor diagrams, what we'll take in, so here having the this like this, okay, so that is E1 is having high voltage and E2 having the less voltage. So E1 and E2, okay, so whatever they have in the angle, this is a delta, so delta angle. So the in between, okay, the angle between E1 and E2, that is delta. So here the current, so whatever the load current, so that we are considering as a I, and it's a different, okay, difference between the voltage, that is EL, okay. Now, so due to the sulfurous, okay, so high amount of power in this generator, okay, remaining power also flows to the generator too, okay. So thought having apart from the generator to load, okay, some amount of power also flows to the generator to generator 1 to generator 2, okay. Now here we are considering the, so what will happen when real power is there, okay, so we are considering the real power, how it will be affected in this transmission line. So here we are having the generator 1, okay, and generator 2. So in between how real power is flowing, okay, how reactive power flowing, okay, that we are going to discuss now. So here what happened, so the real power, okay, the real power in between the lines is P is equal to, okay, we are taking as it, okay, P is equal to, okay, here we already written, so active component and reactive component, okay. So here we are considering along with it, so we are right, that is, okay, even even of flow in a, we are considering to E1 E1 into IP1, and whenever having the IP, okay, so here is that is E1, and coming to the, okay, so okay, this line, so here we are considering the this line, so in this line what happened, so here the amount of power is flowing, so this the line and this is the phasor equation. So now coming to this representation, here we are representing in this line. If you see this line, okay, in this phasor diagram, we can easily conclude what are the components of this component. So what we have in here, we are having the here we are having the E1, here having the E2. Okay, so having the E1 and E2, in between the E1 and E2 having the angle is, that is delta. Okay, the power. Okay, so whatever the current is there, okay, the active component of current flow, we are considering the IP1. Okay, that is IP1. Here we having, just wait. So here having the, that is power is equal to P1, P is equal to E1 and P1. Okay, from that one value having, so here having the this one, right? So whatever the power is there, okay, that we are represented, that is the in terms of the power. Okay, so here in the for generator 2, so for this one, so we are having this. So while we are taking, so E1 and E2, okay, and we are having the E1 and E2. So E1, so here having the E1, this is the line, okay, E2 is the this one, okay, that will be flowing this one. Okay, active current we are considering the in this slide. So if we take the active current, so current also flowing in the same line. Okay, so whatever the voltage is flowing, okay, that's we are flowing the in this line. So here whatever so whatever the power is there, okay, that is, and here having the E2. So here having the E, okay, here having the E2, and here having the E1 and I1. So for this one having the IQ1. Active power is flowing in this along with the in phase with the transmission line, whatever the voltage is there. Okay, so here ordered E1. Okay, so E1 is there. Okay, current. Okay, say current, active current of flowing in this line also, and reactive power we are considering, that reactive power having the, that is here. Okay, that is 90 degrees phase shift with the active power. Okay, so here from equation we are writing, that is here we write in already equations E1 equal to, okay, that is active power at the E1 is equal to P1 is equal to E1 into E2 sin alpha by sin delta. Okay, this is the delta. Okay, angle, that is sin delta by alpha by x. So here is the active power of the at the E1. Okay, and similarly coming to the here for the consideration for the E1. Okay, the power, okay, the common, so active component current, that is IP1 is equal to E2 sin delta by x. So here whatever the x value there, okay, if you change the impedance value, that x is nothing but impedance. If you change the impedance value, so we can change the active component. So if reactive, if we consider the reactive power, okay, so reactive power also it varied with the E1 and E2. Okay, so by that one, so what are the reactive components there, okay, that we have to control by using the value. Okay, so whatever the load angle is there, okay, that is this delta. Okay, if load angles, that is delta is varies with one. Okay, so whatever the load is there, okay, the angle between the E1 and 2, if it varies with the 90 degrees, okay, should be in limit of 90. So if you vary that one, okay, what will happen, the power also will be increases and decreases. Okay, that will be shown here. Okay, if you here consider, so here what happen, the power and angle, okay, the power angle should be in a, so what happen where the 90 degrees there, okay, so beyond the 90 degrees what happen, it will be decreased. So if we having the high, so if it is above 90 degrees, what will happen to the fault on the fault. So it should be in a limit of, while it is 0 to 90, that is power is increasing. Okay, whatever the delta angle is there, okay, that delta angle should be in a with limits of 90 degrees. So if you limit the above 19, what happens, the power flow will be decreased. So here, so the E1 E2 should be, okay, whatever the E1 E2 should be, okay, in this transmission line, okay, that will be varied with the x value. So if want to increase the power in the transmission line, okay, vary with the angle, okay, so that is delta as well as impedance. If it is impedance, if it's control, okay, if we control the impedance, okay, then only we control the angle. Okay, so by different values of and x values, okay, here power will be varied. Okay, so this is for x1, this is for x2, this for x, for different values of x, that will be varies with this one. Okay, for active power we are having the sine. So for reactive we are considering the cos. Okay, for IP the okay sine delta, and for reactive power that is E1 minus E2 cos delta. Okay, by x. So this is for the at the coming to the E1. Now considering this is the if you considering the at end E2. Okay, while considering the for line 2, whatever the less amount of power. Okay, so what happened here, similar also here active component the current. Okay, active component at the E2. So what will happen, E1 sine alpha. Okay, sine delta by x. IP2 is also E1 sine delta by x. So it's similar to the whatever the power is there, because surplus amount of power is transferring from the generator 1 to generator. So same that because the active that is sine reactive component is I2. Okay, reactive component current that is at the E2. So that is the E2 minus E1 cos delta by x. Now if you take the IQ1, so what happened, E1 minus E2 cos. So in this one, so E2 minus E1. Okay, that is the difference. Now coming to the active component. Okay, active P2. So active power is nothing but at the E2, whatever the active is there. Okay, that is we are considering that is power 2 at the E2. That is E2 into E1 sine, because whatever the surplus amount of power is there, okay, that will flow from the generator 1 to generator. So we have to considering the E1 also. Okay, now coming to the reactive power at the E2. Okay, total reactive power. So here is the active power, here is the reactive power while considering. So E1 of, okay, total E1, that is, and reactive component between the E1 and E2. Okay, so reactive power from the E1 and difference between the E1 and E2. Okay, that will by impedance. So if you control the impedance value, the reactive power also control. Okay, if we increase the, okay, what happen, what impedance if you reduce, okay, the reactive component. Okay, so by controlling the impedance, so we can control the reactive power and active power. Okay, that's the main thing. So here what we are doing, by using the fax devices, what we are going to do, we are controlling the impedance. Okay, we are controlling the impedance in the transmission line, as well as we are controlling the voltage. Okay, so by different values for different different component, that is power electronics device combining that. So what we are going to do, so we are going to increasing the, that is, current in this transmission line as well as voltage by using a uh, series injecting. So by using series injectors we are increasing the voltage in the transmission line. By using the shunt injectors, what we are doing, we are injecting the current in the transmission line. Okay, from that one what we are doing, so we are increasing the power stability of the transmission line network. Okay, this is about this. Now at what limit we have to consider? Okay, at what limit we have to grow? So if we continuously increases, okay, so if you increase the reactive active power continuously, what will happen? So the whatever the voltage that we also affect, okay, it should be in a, with a limit. So whatever the delta is there, okay, so the delta angle should be in a 90. So if you increase the above, what will happen? The power flow will be decrease. Okay, that should mean a should be limit. So that we have right here. Okay, there. So high speed control of any of the parameters. Okay, that is we are right. E1, E2, E2, E1 minus and X and L. So transmission line can be utilized only to a below, only to a level below that corresponding to 9. Okay, that should be in a with the limits of 90 degrees. So if it above 90 degrees, what will happen? It will go to the reduce the power. Okay, that should be in a with a limit. Okay, this is all about the power flow in a mesh network. Okay, as well as power flow in a dynamic stability consideration. So if you increasing the continuously increasing the current flow, okay, what will happen? It will directly, so whatever the current flow we are injecting, okay, in this transmission, okay, by using the shunt injector, what will happen? So it will have the one current, what initial that current is I. Okay, if you go to the inject in the current, okay, that will be I2 will be having the, it will goes to continuously increasing means that will goes to the perfect perpendicular to that one. Okay, resultant one, it directly perpendicular to the E2. Okay, that will happen continuously inject. Okay, that should mean with a limit. So whatever the resultant current we are injecting, that should be in a limit. Okay, not in the above, not in the below. That's why whatever the fax devices we are using, that this should be in a with a permissible limits only. Okay, okay, this is about our class.